Okay, so you told me we already talked about charging by friction. Here's some like official notes on that. It's actually really difficult to tell when we rub two things together, like which thing becomes positive and which thing becomes negative. I mean, kind of through like process of elimination, we've like figured out which thing does become negative and which becomes positive. So we just make these lists of things. It's called a triboelectric series. And the way that this works is the stuff at the bottom are quite good at giving electrons away when we rub them. So they like to give electrons away. And then the things at the top of the list are pretty good at receiving electrons, or taking electrons. So if we rub, well, I guess the best two things would be asbestos, which we don't really want to use. Some forms of asbestos are very dangerous. And celluloid, is that a bio thing? No? Alright, whatever. I think celluloid is like, I'm not going to embarrass myself by even making a guess. If we were to rub this and this together, we would get lots and lots and lots of electrons going from the asbestos to the celluloid. So the celluloid would be negatively charged, the asbestos would be positively charged. So we don't have asbestos, we do have rabbit fur, that's what we used last class. So rabbit fur is also particularly good at giving electrons away. I don't think we have celluloid, but we probably could find some things made out of rubber. Same deal, like the balloons are not rubber, they're latex. But if we did rub a regular balloon, not the weirdo balloons that we played with on Tuesday, if we rubbed a regular balloon with rabbit fur, the balloon would become negative, the rabbit fur would be positive. So the mechanics of that are really complicated, and it's a level of chemistry that I'm not familiar with, but that's all that we can say about charging by friction. Charging by conduction, which we already talked about, just means that we have a neutral thing, we have a charged thing, and we directly touch the two things together, and electrons will go from one thing to the other thing, and then nothing remains neutral. So we charge the neutral thing by touching it with the charged thing. And that's exactly what we did with the electroscope. Was wool on that friction list? I don't think so. Yes, it is. Wool is right here. Now, this is called PVC. Polyvinyl chloride would be up here somewhere. So when I rub the PVC with the wool, we should end up with a negatively charged rod and positively charged wool. So if I touch this negatively charged rod to the electroscope, electrons should move from the rod into the electroscope. Right, boom, there we go. So that was charging the neutral electroscope by conduction. All right, other questions about charging by conduction? So here's just, two examples you can look at when you're studying. So here we have a needle electroscope, we have a negatively charged object. The electroscope starts off neutral. We touch the negative thing to the electroscope and electrons go into the electroscope. They distribute everywhere within the electroscope because it's made out of conductors, and now we have two negatively charged things. Is this negatively charged sphere a conductor or an insulator? Look at that. Look at that for 10 seconds, right? I think we have evidence to say whether this thing is a conductor or an insulator. Look at the pictures and see if you have a hunch. All right, see if, talk to your foursomes, see who has hunches and who doesn't and what the hunch is. Oh, we didn't play with this one yet. We'll play with this one next. Okay, conductor or insulator? No. Conductor, why? Because what, Akansha? Oh, we could do that if it was an insulator. Right? We did that right here. We had this rod as an insulator, right? And it still gave electrons to the electroscope. Magna, how do we know it's a conductor?
Well, the electrons are kind of evenly spread in the sphere.
In which diagram? 1, 2, or 3, or all of them?
Well, 1 and 2.
Well, 1 and 2,
Oh, and 3.
we could put charges evenly on an insulator. It would be a little tough. Like, we didn't do it when we were charging this thing. We probably put them evenly, like, around it, but not throughout it. But no, I think we could charge it like that. I think the more important one is in what happened in between diagram 2 and diagram 3. If this sphere was an insulator, we only would have discharged the part of it that was touching the electroscope, right? Because charges can't move in an insulator very well. But we apparently took charges off of more than just right here, because we used to have like 10 charges, now we have 3, and still we have an even distribution of charges here. If this metal thing was an insulator, we would have something like, you know, that, where we've only lost charge from the part that touched the electroscope. All right, so that's another example of conduction. Let's do one more, and then we'll move on to our other method of charging for today. So here we again, this time we start with a neutral conducting sphere. What is that? Boat, a hat, a UFO, what is that? It's a boat, a toy boat, fine. So we have a positively charged toy boat that's a conductor that we touch to the neutral conducting sphere, and delocalized valence electrons from that metal sphere are going to be attracted into that positively charged boat, right? That will cause this neutral or this conducting sphere to become positive, and it actually makes our boat less positive than it was before because it picked up some electrons, right? And then we can pull it away, and we have a less positive. It's actually an aluminum pan. We have a less positively charged aluminum pan, and now a positively charged conducting sphere. And again, that's charging by conduction because all we did was touch the neutral thing and the charged thing together. Anytime that we charge by conduction, our neutral object is going to get the same type of charge as our charged object, right? The neutral thing became positive, and we had a positively charged pan. And here the electroscope became negative, and we had a negatively charged thing. All right, any other questions about either of those sequences of charging by conduction? Okay, great. So now let's charge by induction. And when we charge by induction, we are not going to have direct contact between our charged object and our neutral object. All right, so when you are ready, come on up again. This time we'll play with a leaf electroscope, or maybe we'll play with all 3 of them. I feel like holding stuff this time. Good enough. Are you going to focus or what? Yeah, good. All right, so I do have 3 different electroscopes. Some of them are, well, this one you really can only see from like the 2 ends of it. That's fine, whatever. We're going to charge all 3 of them up. I need these ones. So we're going to charge this one up again, and I'm going to bring it close, but I'm not going to make it touch. Oh, come on, seriously? Worked great yesterday. Oh, that's not. I see. All right, that'll work. That'll work great now. All right. Come on, you. These ones work? That one worked pretty well. When I touched it, that one worked okay when I touched it. Yeah, we didn't get to see those ones yet, so make sure you get to see at least one of those. Where now this one only has a single leaf, that one has 2 leaves, but they're definitely deflected. Does this work? This one works if I touch it. I think I know what the problem is today. What's the problem today that wasn't a problem yesterday? It's like a lot of water in the air. And not only is there a lot of water on the air, but there's a lot of water on the outsides of our insulators, making them a little bit conductive. Might have to pull out the rabbit. I didn't want to. No, you know what? My eyes were getting itchy the other day. And there was like just a coating of like rabbit fur over everything on my desk. All right, so I did get a response this time. Now,
It's rabbit.
I'm actually going to try, before I get the rabbit, I'm going to try something different. I'm going to use a different PVC rod that I know I can charge really effectively. I can hear.
Oh, you
I can hear the static electricity, which we'll talk about in a few minutes. This is really charged. It's going to work great. All right, watch the electroscope now. Oh, did you hear it?
Yeah.
If you heard it, that's a problem. So the electroscope responded, but then watch what happens when I take it away. I can actually feel it pulling on my hair.
Oh yeah, it's
Some of your hairs are sticking out.
So did I charge the electroscope? Kind of. Kind of answer is kind of. It's not charged. It is not charged. It's neutral.
Charge.
No, it's not.
Not even a momentary charge? What is that then? Magic?
No.
Like, is it
The electroscope is neutral. The electroscope is neutral.
So,
Oh, it's the separation of charges?
But we have a separation of charge within the electroscope. All right, so my PVC pipe is negatively charged, right? Negatively charged. So I hold it near the top of the electroscope, and what happens within the electroscope? Don't say all.
something like
Some delocalized valence electrons from the top get repelled down to the bottom. All right? So the bottom half of the electroscope is negatively charged. The top half is positively charged, but there is no net charge. And we know that because when I take that away, those electrons that book down to the bottom go back, up towards the top. Right? So I never charged this, but I induced a charge separation within the electroscope. All right? So we're not done because we still haven't charged this thing, but are there questions from anybody about some of the electrons have moved down to the bottom right now, but they move back up when I take that external charge away? Great. So now let's finish. Let's finish the process. Let me get a nice charge on our rod again. I don't hear it this time. That's interesting.
got the magic gears.
All right. So I'm gonna induce the charge separation again. Ruchi, can you touch the very bottom, not the needle, but the very bottom of the electroscope? Yep. Go ahead. And then take your finger away. And now it's charged. What do you mean what?
That makes sense.
It's simple.
It's real simple.
It's simple. Let's discharge the electroscope. Maybe I can do it by just touching it, maybe not. Yep. Close. Why am I grabbing the pipe?
You transfer your charge into the metal.
Yeah, so where does the pipe go?
To the ground.
Pipe probably goes underneath the school, like into the ground. If not, it at least goes throughout the entire school. So it's big, right? School's big, ground is big. So whatever charge is on me, hopefully can go into the pipe, into the ground. When I do that, it's just not working very well. All right, so let's get this thing back neutral. Great. So let me induce that charge separation again. So I cause some of the electrons to go down to the bottom, and then Ruchi touches the very bottom, and some of those electrons go into her. Right? So this is not neutral anymore. It started off neutral, we induced a charge separation, but then Ruchi stole a whole bunch of electrons off the bottom. So this is now charged, and is it positive or negative? It's got to be positive because it gave some electrons to Ruchi. right? So we charged the electroscope by induction. So we didn't actually charge it with our charge thing, but we did have to touch it with something. Right? We had to touch it to something that could take some charge away. So that's called charging by induction. And when we charge by induction, we can charge our neutral object with an opposite kind of charge than we introduced to the system. All right, and in fact, let's just do an example of that before we maybe try one of the other electroscopes. Come on. Good. We got most of it away now. And we'll go back. All right, this time, Brian, can you please touch the top of the electroscope and keep touching it. All right, now you can let go. Ah. Is it charged?
Yes.
No, it's not. Look at it. The needle's still pointing up and down.
It's not charged.
So what? Ruchi's special, Brian's not?
No, Brian touched the top and he
Oh,
felt it.
all right. So if he touches the bottom, then it will work.
No, it won't work.
Let's see. All right. So Brian, this time you'll do the same thing, but you'll go ahead and touch the bottom. And let go.
Well,
will
he
work.
held on test.
Yeah.
Right. So did electrons ever go into Brian?
No, it's not.
All right, touch the bottom again. Electrons absolutely have gone into Brian. But they went back into the electroscope when I removed the rod, right? So you can let go now. So when I held the rod here, electrons definitely went from the top down towards the bottom. Brian touched, they went into him. But as soon as I removed this, now, right, we have the top of the electroscope is positively charged until those electrons go back in to neutralize it. So we did not do it correctly in order to get an electroscope that would remain charged. All right, but I want to go back to Brian touching the top. This time we'll make it be similar to Ruchi. Okay, now you can let go. All right, and now the electroscope should be charged. It is, but I'm surprised it's not more charged than that. The electroscope is charged right now, and is it negative or positive?
Positive. Brian took it away.
Let's analyze it again. All right, let me discharge it, and we'll go through it again. Brian, you touched the top that time, right?
Yes.
All right. So right now, electrons have migrated down towards the bottom. So the bottom of the electroscope is pretty negatively charged. The top is pretty positively charged. So Brian touches the top. Go ahead. And he's touching a positively charged thing. So he is giving electrons to the positively charged thing. Let go. Right, so Brian gave some electrons to the positively charged thing. So it should be negatively charged now, except something weird happened. It didn't happen before, but something weird happened this time. Right? So it actually does depend on where we touch it. That time we charged it by induction, but we got our neutral thing to have the same kind of charge as our charge thing. So for induction, we can charge our neutral thing either way. For conduction, we can only ever charge it with the same type of charge, be that positive or negative. The same thing can happen with the leaf electroscopes, except we're only able to touch the top. We can't actually touch the bottom. Yeah.
So if we were to touch the bottom of that, would it, while you were doing it by induction, would the charge be different?
Different from if you
Like-
touch the top?
Yeah.
Yes, it would be opposite,
Okay. Because you're
as if you touch the
taking
top.
the. Okay.
That's right, because if you touch the bottom, right, then if this was negatively charged, then you're touching the negatively charged part, and electrons will go into you. If you touch the top, then you're touching the positively charged part, and electrons from you will go into it. So
Okay.
yes, it is opposite whether you touch the top or bottom. There should be a magic spot in the middle that actually isn't, that we didn't induce a charge in, right? If the electrons go to the bottom, leave the top, there should be some spot in the middle that's neutral, and if we touch that, then nothing should happen at all. All right, so let's have a seat. We'll actually look at a couple of cartoons of what we just did. But that's probably the most complicated thing for today, is charging by induction. this point, I think I could put Rachel in the back. All right, Gucci, Jack, Ben. So this is not identical, but it's very similar to what we just did with our electroscope. Here we are starting off with two neutral conducting spheres that are touching. And what's this red thing? The balloon, right? There's a balloon. And we actually did manage to charge some balloons on Tuesday. We just somehow couldn't get similarly charged balloons. So balloons are made out of latex. Latex is pretty good at taking electrons from things. So this balloon should be negatively charged right now. We hold it near one of our neutral conducting spheres. If it's charged, I should be able to get it to stick to stuff. Yeah. I have a feeling that there's a coating on these balloons that makes them a little conductive. We bring our negatively charged normal balloon near the neutral conducting sphere, and that repels some of the delocalized valence electrons in the conducting sphere over to the opposite side. So we will have a migration of negative charges to the opposite side. And then if we pull this conducting sphere away to isolate it from the first one, that's now negatively charged, and it's going to stay negatively charged, right? We even have the charges kind of distributing themselves so that it's pretty uniformly charged, and then if we pull our balloon away, the positive charge will kind of rearrange itself on this one as well. So we never touched the balloon to our conducting spheres, yet we were able to charge them by induction. We actually did it without Lucci or Brian, but we did have two of them to work with. Follow-up questions about that sequence of steps to charge those by induction? All right. And then, so what did we 9:58, we have, what is that, 15 minutes, right? All right. Here's another example that's a little more similar to what we did with Rucci and Brian. We start with a single neutral conducting sphere. We bring our negative balloon nearby. Remember, we're not touching, we're just bringing it near. We again cause that migration of negative charge away from the balloon because there's an electrostatic repulsion. And then Rucci comes over and touches that side of the sphere. Electrons will go into her because she's quite a bit bigger. They can spread out more. And then she stops touching it, right? We can remove the balloon, and we end up with a positively charged thing. All right, so very similar to what we did with the electroscope. Any follow-up issues with that sequence of events that led to charging by induction? Great. Yeah, we can play with this for minutes. So what is our fourth way of charging? I think we made passing reference to it last time. Lightning. Okay, we did make passing reference. Great. Let's just take 30 seconds to do that. Okay. Let me turn one set of lights off so we can see a little better. Alright, so who's this? Sure. It's a sweater, and what are sweaters usually made out of? Wool. Wool, and we know that wool is a pretty good electron giver. And what's this? Balloon. Balloon, right. And what's this? Lightning. No. It's a wall. Not
It was yellow.
Exciting as light. And how do you think the sweater is charged right now? Neutral. It's probably neutral. How does it look like the balloon is charged right now? How does it look like the wall is charged? It actually looks like it's positive. What we actually have here is a red positive sign with a blue negative sign right on top of it. So it's actually neutral as well. And if we move the, so sometimes, well, my weird balloon didn't stick to the wall. But should this balloon stick to the wall? No, it should not, because it's not. Well, it did. It did just because it stays there. Like it it sticks to the air too. It shouldn't stick to the wall because, well, it's a helium balloon, so it's not falling down, but it's not charged, so neutral things and other neutral things don't exert a force on each other. So let's make the balloon become charged. So what do I need to do? Rub it against the sweater, right? And now it has taken, it took balloons from the sweater and it's attracted to the sweater because it's negative and this part of the sweater is positive, so it actually does like to stick to the sweater. But if I bring this near the wall, notice that the wall charges do react a little bit. The wall is probably a conductor or probably an insulator. It's probably an insulator. And insulators are not, the charges are not mobile, but they're a little bit mobile, right? The electron can move to like one side of its atom. It can't move all the way to the other side of the wall, but it can move a little tiny bit. So that's why if we shove the balloon right on the wall, it will stick, because we can force a few electrons further away, and now we do have a positive, slightly positive region of the wall next to our negative balloon, right? So yeah, we can get the balloon to stick to the wall a little bit. Anything else you want to do here? Yeah, me neither. All right, so let's briefly talk about our fourth method of charging, which we can't talk greatly about until we actually dig into chapter 21. So our fourth method of charging a neutral object is called charging by lightning. And in order to do that, we need extremely large accumulations of charge. So we probably can't do it with a balloon. It's not completely out of the realm of possibility, but we probably can't do it with a balloon. We actually probably can do it with my PVC pipe, but it's going to be very unimpressive lightning. But we actually can do it. So if we have a large enough accumulation of charge, so I said with my PVC pipe we can do it, the PVC pipe should be getting negatively charged. If we get enough coulombs of charge, or enough millicoulombs of charge on there, what's sitting next to the PVC pipe? Air, which is what?
Insulator.
It is an insulator, but what is the air made of? Nitrogen and oxygen. All right, let's pick on the oxygen for a minute. If we get that, and the oxygen molecules, positive or negative? It's neutral, right? It's neutral. Right? It's not ionized normally. Right? If it is, it's extremely reactive, and we would immediately oxidize something else to regain that electron. So no, it's neutral. But if we have a big enough amount of charge next to it, then we can ionize the oxygen. It probably actually makes a little more sense if we have a positively charged region of space. We can do it with a negatively charged region of space, but it might conceptually be a little bit easier if we have a positively charged thing. That positively charged thing can rip an electron off of the oxygen. And if we do that to enough air molecules near our charged thing, we actually don't have a gas anymore. What do we have? We have plasma, right? Plasma is just charged gas. And plasma is an extremely good conductor. So if we have a big enough charge accumulation, we can cause the air surrounding it to be a plasma, and then all of a sudden discharge that thing, right, to something. So that's all that lightning is, but we need a huge accumulation of charge to do that. All right, so I brought a few new things out the other day. This is the best lightning generator that I have. Lightning is always a little bit prettier in the dark. So I'll show you what this does, and then we'll turn the lights off when it's time to get the lightning. So this has a crank that I can turn, and all that does is makes these two wheels spin in opposite directions. All right, so all that the crank does is introduce some like angular mechanical energy. And then there are some copper brushes, and some of those copper brushes, like this one, and there's two on the other side, are touching these little metal spots on the wheel. So we are getting charging by friction when these copper things